Okay, ladies and gentlemen, let's take a look here. What's going on? I want to remind you all that we record the lectures, and they are where? They are under the module section titled Lectures, and then they're listed by the date. Is that right? Yeah. Good. Okay. Now, I'm going to go to 261, and we're going to take a look a little bit about chain rule notation for you guys. And, maybe in the future I'll make a video of this. Where are we at? Derivative chain rule operator notation. So I started to give you guys already some operator notation. Is that right? Do you guys know what I'm saying? So let's do a little bit more of that, because it transitions nicely into, where we're headed. So I just want to share with you guys that location in case you wanted to know. We'll put it in the comment section. And I'm looking at it right now. So let's give you guys somewhat. How about this? Let me go back. Where am I at? Let's go to www. I'm going online here. So let's see. I'm going to have you guys try some of these out. How do I change that? Derivative of cosine squared 2. Differentiate cosine x squared and 3. How about the square root of cosine? Okay, and 4 yeah, we'll do this. Okay. So I'm going to have you guys warm up with chain rule notation for these functions, and we'll see how it goes. Okay? All right, let's get out the clock. If I can find it. Let's see what you guys get. Okay. So this is chain rule, and I should say with not notation, but yes, it's notation. Let's be more specific. What kind of notation is this? Operator notation. Okay. All right, now let's see if you guys know what we're talking about with this. I know they're all cosine, but you know, just you guys can compare and contrast these situations here. So I think what's important to note for people is what? What does that mean if you have cosine with this power 2 there? You guys know what that means? Sometimes people don't know what that means in terms of their notation. So let's kind of talk about what that means. Okay, that means you have what? Cosine to the second power, by definition. Okay? All right, you guys see the point. What is happening then is cosine is your base and 2 is your what? Power. Is that right? So how do you guys handle this? Remember that kind of, remember I give you this sort of situation here? You got what? If you have a, this is really power rule, right? So it's n triangle n minus 1 times the derivative of the base there. This is referred to as the chain. Okay, if you guys remember that. Here's your what? Chain. So this is the power rule version. Now what does that mean? Well, it means I have 2 cosine of x, okay, 2 minus 1, which is 1, but by the chain, differentiate what? Cosine, okay? You guys okay with that? And now what's the derivative of cosine? Negative sign. So ladies and gentlemen, all together, you end up with what? Here's what you guys end up with. It's going to be what? 2 cosine x, excuse me, minus sine x, and put the negative sign in front. So 2 cosine x, sine x. Ladies and gentlemen, there you go. Easy peasy what? Lemon squeezy. Yeah.
Can we write it in negative sine 2x?
Negative sine, no, it depends what you mean by negative sine 2x. This 2, so you guys know, that 2, this constant never gets multiplied to what's inside the argument. This is,
Yeah, but you can transform it using like trigonometrics like a
okay, no, but let me finish that, just so some people think that, can I ever multiply 2 with the x or any? No, it's functional notation, like f of x. Can I write an equivalent identity here? You can, but you don't have to. This is just really what? Can you work with operator notation for chain rule? Okay. And this is probably something that I have not shown people really yet. So this is why I'm doing it. I'm showing you guys now. Okay, you guys see my point? So you say, okay, I think I've shown you something like this, though. But my point is, can you compare and contrast? Can you apply that? You know the difference, right? So now you say, well, what do you mean? Because I want you guys to compare and contrast all of them. What about this here? What am I looking at now, taking the derivative of cosine 2x? Well, if you have cosine of a function, you say, what's the derivative? Derivative of cosine is what? Negative sine of that function times the derivative of the argument. What's inside, right? So this is a different situation than what you guys see here. Okay, it's a different situation. So I want to share that with you guys. And so that means I have minus what for a derivative? Minus sine of x squared. Now times, this is the chain again, the derivative of what? X squared. So again, sometimes people, they never deal with the derivative of the chain. This is kind of thought of as the chain. And that derivative is what? 2x. So altogether, you're looking back at the book, you see minus 2x sine of what? X squared. That's what you'll see. Okay?
So we're using triangles to like represent what's inside.
Yeah, I use the triangle. You can use U. You know, the book, and sometimes, people say, I'd rather do what the book does. The book might have it this way. This is the U. This is the U. And then that's U prime, which is du dx. So there's various ways to do that. I'm just going back to the Jaime Escalante version where he wrote that with triangles.
But it's okay. We could like use any font, right?
Yep. Number 3, ladies and gentlemen. Number 3 is a little bit similar to number 1. Why do I say that? Number 3 and number 1 are very similar. Do you guys know why? Why is that similar? d dx of what? What does that mean? Well, you still have cosine, but now the power is what? 1/2. So the base here is cosine now. Okay? So you say, is this my base? Yes. And then what's the power going to be? 1/2. So ladies and gentlemen, you're back to using what? The first one. Okay? So you're back using this. Now, what does that mean again? Well, we have to use the power rule, right? Which is going to be what? 1/2 cosine of x. Put that in your parentheses. 1/2 minus 1. Now the chain, the derivative of what? Cosine, which you guys know is really going to be what? Minus sine. So do the arithmetic. Isn't that 2 over 2? So I get 1/2 cosine, and that's minus 1/2 times negative what? Sine. Minus sine over what? 2 square root of what? Cosine. Is that true? Yeah. And there you go. I guess we're highlighting it blue. So double check, ladies and gentlemen. You guys are good with that? Does that seem okay? What do you guys think? All righty. All right, let's try this one here. You say, oh, how is this question? It's very similar. Okay, so this is going to be, again, here's my base, and then here's my what? Power. Is that right? So we're going to use, again, power rule with chain rule. Okay, you guys with me on that? Okay, so you say, what does power rule with chain rule work? How does that look? That's 1/2 again. Cosine 2 pi x to what power again? 1/2 minus 1. Don't forget your chain. And that's cosine 2 pi what? X. You got to take that derivative. So here is the chain, ladies and gentlemen. Okay? Just like up here, this was the what? The chain. Okay? Here, this was the what? The chain. And everybody forgets that. They go, nope. Chain. So every one of these had chain there. So notice this here. This derivative, we'll say, what is that going to be? Well, now I have to use what? This. Is that right? And you say, well, I don't like the u. Okay. Okay, do you guys see my point? You say, okay, what's the derivative of cosine of that 2 pi x? Well, it's minus sine of what? 2 pi x times the derivative with respect to x of 2 pi x. Is that right? Don't forget that this also has a what? A chain. Okay, you guys with me on that one? You're differentiating cosine 2 pi x. So now, what's the derivative of this 2 pi x? You guys know that's going to be what? 2 pi. But don't forget everything that you have here. Don't forget we have this portion here. I'm going to go back to highlighters. I have this component, not to forget. Okay, I have this component, not to forget, and then I have this component. Okay, so double check, take a look, get a good look. Okay, so let's kind of not forget the gray. So that'll be, if I write it down, 1/2 cosine 2 pi x, that whole thing to the minus 1/2 power, okay, times negative sine 2 pi x times 2 pi. So I would say to you, what? Don't the 2's cancel? So we're going to have negative pi sine 2 pi x as a numerator over the square root. We'll put that as a square root here of cosine 2 pi x. And that negative sign you can see in back of the book right here in front. So anyway, and there you go, ladies and gentlemen. Okay, what do you guys think? Is that easy peasy lemon squeezy?
Depends.
Well, let's try this out. Let's see if you guys are awake. Derivative of sine cube of pi x. Number 6, I'm going to look back at my, where is it? Where'd it go? Derivative tangent of 1/2 x 3/2 power here. Number 7, derivative of secant of tangent 3x. Actually, let me change that 3. Okay, just to compare and contrast. Square root of x.
Professor, what's the power of like
3/2. All right, now, just like before, what are you guys really looking at here? Okay, this is going to be what? Power rule. So I'm going to go back and find that power rule again. It's really power rule with chain rule, right? Okay, so you say, well, what does that give us? That's going to give us what? 3 times sine of pi x. Okay, and then that's going to be 3 minus 1. Is that true? Now, don't stop right there. Let me write pi x a little clearer. Don't stop right there. You now have to differentiate. Don't forget the chain. Sine what? Pi x. So do not forget your what? Chain. But when you differentiate here by the chain, or I should say differentiate the chain, you're going to say, what is this? Well, you need to have another function, I think, right? I think we wrote this down last time. Now, I don't know. Would you guys prefer letters or do you prefer the shape?
Maybe shape.
Doesn't matter to me. You guys see my point? So, if I just said to you, here is, oops, sorry. If your function is sine u, maybe you prefer that. The derivative is cosine u times what? Du dx. So the derivative of sine will be what? Cosine pi x, but now again, don't forget to differentiate pi x with respect to x. Because again, you have another chain right in here. So the chain portion. You need to know the derivative of pi x, which is going to be what? Pi. So just make sure, ladies and gentlemen, that you go back and remember everything that's what? Here. You don't want to forget any of this because it's all part of your answer. And then, of course, what's 3 minus 1? Isn't that 2? So I would start off by writing things down again by saying that's 3 sine squared pi x times cosine what? Pi x times that pi. So now you could put your constants together and say 3 pi sine squared pi x cosine pi x. There you go. So double check, ladies and gentlemen, if I have every detail here. But this is chain rule, again, even within chain rule. So notice I'm following all of what to do by just using my operator notation. Okay, you guys see that there? You see every detail? Operator notation. I can do that in my sleep now. Because all you got to do now is practice, practice, what? Practice. Okay. So this is tangent of what? 1/2 x raised to the what? 3/2 power. Okay, and then you're going to use what again? Maybe you want to see it this way. If my function looks like this, maybe I don't want to see those things. I want to see it in terms of u. I think, does the book do it that way? Okay. So, 3/2 tangent 1/2 x 3/2 minus 1, and then don't forget the chain, okay? Because the chain here right? This portion here is what we call the chain and chain rule. So I'm going to have to differentiate now tangent 1/2 x. Don't forget, 1 is 2/2. Okay, now, again, I don't think we have the chain rule version here, but I'm going to write it down here for you. Okay? So if your function is tangent u, I'll switch to that, to the book notation. What's the derivative of tangent? So it's secant squared u times du dx. Again, the what? Chain. Okay? So this portion is going to be, for us, derivative of tangent is secant squared 1/2 x. Now, again, chain rule, take the derivative of 1/2 x. So I'm really using the book's notation. And what's the derivative of 1/2 x? Isn't that just 1/2? Okay, so highlight your terms, because you can very easily what? Forget what's really here. All right, so now, what's 3/2 times 1/2? Right? You might say, what are you doing here? Well, I take the constants. 3/2 times 1/2, isn't that going to be 3/4? 3/4. Tangent 1/2 x. 3/2 minus 2/2, isn't that 1/2? So that's a 1/2 power there, times secant squared 1/2 x. And you might even see the 1/2 gone. They might even just put what? Square root. So, ladies and gentlemen, here's your answer. Again, using what? Chain rule. Okay? Every gory detail. What did you guys think? You said, boy, they can have me do chain rule within chain rule even? Yes. Let's see how this one goes. Is this one kind of scary? Well, what do we have to do this one? Right? If the book says you have secant of u, the derivative is, what's the derivative of secant? Secant tangent, right? And times du dx. So you say, is that secant tangent square root of x times tangent square root of x? And don't forget the chain. The derivative of what? Tangent square root of x. So this is the chain here, okay? That's a chain and chain rule. So don't forget that. It's the chain and chain rule. So secant u, tangent u, du dx. What you have to use now, again, here, what's the derivative of tangent of u? Okay? So I'm going to say, if your function's tangent u, the derivative is what? Secant squared u times, by chain rule, du dx. So it's operator notation and chain rule again. So that portion will be tangent square root of x. Oops, not tangent. secant squared square root of x times, by chain rule, the derivative of square root of x, square root of x. Now, what's that going to be? And there it is. There you guys go. So we just have to write everything down together now, okay? Okay. So what I'm going to do here is I'm going to copy this because we're completely out of space. Copy that. Okay, we're out of space there. And then this is times what? Don't forget it's times what? Secant squared square root of x times that 1 over 2 square root of x. So, darn it. It's going to be odd notation. I'll put it this way. Put it as a denominator, okay? But don't forget, this is that multiplication here and here. We just don't have enough space here. Okay? So there you go. Okay? All right. Operator notation. Now, you might say to me, why did you want to review all this today again? Chain rule with operator notation, go over some additional examples. Well, there's always a couple of reasons. I think it's good to see these things because you might see them in some of that book work. Is that right? Did I assign any book work for you guys?
Yes, you did.
Oh, thank you for noticing. I even sent that. I sent that to you all. So I did put some of this there. It might help you with some of your book work, you guys think?
Yeah,
That's the whole idea.
because like for homework, there are like several, like it's mainly about triple,
Yeah.
like chain.
Yeah. That's why I'm doing what I'm doing. You go, boy, Mr. Judge, you put that in some book work and you're reviewing some of this stuff for my benefit? Sure. All right, so this is why we're doing what we're doing. But also, ladies and gentlemen, I want you guys to remember something here. This is the second reason I'm doing this, okay? Does anybody know what this is? If I write down this x squared plus y squared equals 4, do you guys know what that is, by any chance? What is that? Thank you. This is known as a what? Equation of a what? Circle. Centered where? Good. At the origin with radius what? 2. You might say, is it really? Yeah, because the equation of a circle centered at the origin is of this form here, r squared, where that r value is positive. This is what we're talking about. You know, in this example, the radius, this is r squared here. Okay, and so you say is r squared 4, which means r is plus or minus 2, while your radius is actually what? 2. So this is kind of, you know, the general form for that equation, right? And so you might even look at Desmos and say, hey, does Desmos plot circles? And the answer is yes. Okay. Okay. So, okay, so here's your equation of the circle, ladies and gentlemen, right? And here is the graph of this thing. But I want to actually make a remark here. Okay? This is called a what? Formally, this is a, what is it? It's not a unit circle because the radius is 2. But what I'm looking for is this is known as a what? This is a relation. This is not a function. So you go, what do you mean? Well, if you look at this equation of the circle, this is in the family of curves known as relations. They're not functions. So you say, can I take the derivative this way? No, you can't. Because all these derivatives were given to you. This is a relation. This is not a function here. Right? They were given to you this way. You say, okay, y equals what? F of x, and you had to determine y prime. But you can't do that directly when you have a relation. And what other curves are under the relation? There's a lot of relations out there. You got hyperbolas, you got ellipses, you got, circles. In fact, there's a lot more curves out there that you can write as a relation, and you still need to find y prime, which is dy dx, right? So the question is going to be, when x squared plus y squared, when you're given a relation, how do you find y prime, which is dy dx? And that's where we're at. We're at the process known as, you're going to have to use implicit differentiation. This is, in my mind, this is really an application of what? Of chain rule. That's what this is. This is thought of as an application of chain rule to differentiate a relation, meaning finding dy dx. And the process is, well, I don't want to say it's a simple process, but there's a process, right? So here's what I'm going to say to you guys. Step one. Step one. Take the derivative with respect to x of both sides. This is what they mean. This is use operator notation. So, a very simple kind of thing. So when I say derivative of both sides, you take d dx of the left, which will equal what? D dx of the what? Of the right. Okay? Maybe that's what you guys need to see. We're going to take the derivative of both sides. This is implicit differentiation. Okay. So now, ladies and gentlemen, you say, well, what does that mean? Well, what's the derivative of a sum? That's right. So we're going to differentiate the x squared plus this differentiate this what? Y squared, and that's going to be the derivative of a constant. Now, good. So pay attention to this detail now here. This is d dx, which means you're differentiating with respect to the what? X variable. Now, what I didn't say here is well, first of all, let's do this here. Can you guys tell me, what's this derivative of 2x by product rule? I'm sorry, I gave you the answer. Derivative of x squared. Told you I could do it in my sleep. The derivative of x squared is 2x, ladies and gentlemen. What's the derivative of any constant? 0. Now, here's where you really focus here. This is going to be interesting. All right? This is the part that's interesting. What I didn't say that you always have to assume, because it's actually true. I can prove it to you. You assume y is a function of x. You see that y variable? It's really a function in terms of x. You can think of it that way. That's the assumption. You see, I can go back and take this original equation and solve for y, and it's going to be in terms of x. Okay? And you get the top portion of the curve and the bottom, but I'm not going to go into that detail this morning. Now you say, how in the world can you differentiate y squared? Well, here's what today had to do with. Have you ever seen anything like this today? Triangle to the nth power, and that n, triangle to n minus 1 times the derivative, that chain of the triangle? Have you ever seen that before? This is why I say you're really looking at what? Chain rule. That's 2y times dy dx, or y prime. This is by, again, what? Chain rule. Don't forget that. So an application of chain rule is implicit differentiation. You got to know chain rule if you're going to do implicit differentiation. Now, that means we have what? 2x plus 2y. I'm going to put times y prime, which is really dy dx. And that's going to equal what? 0. So you're really looking at all the gory detail here. 2x, 2y, y prime, 0. You're looking at what's left here. And I think earlier today we were using the gray. So let's just be consistent. Okay? Now here's the second part. That was step 1. Step 2. It's really a two-step process. You solve for what? Y prime. Y prime's right here by the chain rule. So how would you guys solve this for y prime? Right? Don't you subtract 2x from both sides? And now you have 2y times y prime becomes negative 2x, right? Don't you divide both sides now by what? By the 2y, right? Now what do you end up with? Right? Your 2's cancel, don't they? Yeah. So ladies and gentlemen, there is a way for you to find the derivative, dy dx. We just did. Yes, it's two variables. It's x and y. But ladies and gentlemen, you did your first implicit differentiation here. And you had to differentiate a what? A relation. Notice this. Didn't we say y is a function of x? Well, it doesn't matter. But so, ladies and gentlemen, this is where we're at. We're starting to talk about implicit what? Which is an application of chain rule. And of course, you might say, can I find locations of horizontal tangents? Sure. In this picture, you got a horizontal tangent where? Here. You got a horizontal tangent in this picture where? Here. Okay, so we can find horizontal tangent lines, those locations, meaning these addresses. And by the picture, what could you guys see? This is where x is 0, right? Y is negative 2. Here, this is where x is 0, y is 2. So graphically, I mean, I can find those horizontal tangents. But how did we do it before? Yeah, you set this what again? Derivative equal to 0. Solve for x. So that means, ladies and gentlemen, negative x over y equals 0. What does that mean? That means x is what? 0. Okay, so you can do the analysis. You find the location, find x is 0. You say, well, how do I get y? Well, isn't x squared plus y squared equal to what? 4. So if you plug in x is 0, isn't that 0 squared? What does that mean? That means y squared is 4, or y is plus or minus square root of 4, which gives you y is plus or minus what? 2. So this is the analysis, which is consistent with the picture. Horizontal tangents happen when x is 0, y is 2. When x is 0, y is negative 2. So this is the area where we're headed with some of these derivatives. Just so you guys know, with some of these relations, we can find those locations in the same way we did before. That's all. And I just wanted to share that with you, why you care about a derivative, and then the geometry of the picture, and this is implicit. So we're going to start that this week. So ladies and gentlemen, welcome back with chain rule, operator notation. As you guys can see, we used it here in implicit differentiation. That's the notation of choice. So we're going to continue tomorrow with implicit what? And when do you use it?
Yesterday.
When do you have a relation? Those of you guys who have taken pre-calculus. Anybody take that course? I don't want to ask. I don't want to know. Anybody take pre-calculus? When do you have a relation? Well, we'll see tomorrow. Okay, take care.